I'm kind of excited because today I get to talk about the fundamental theorem of calculus, which is really what ties all the things we've been studying together. We've done some work with antiderivatives and indefinite integrals. We've talked about approximating the area under a curve with Riemann sums. And now we're going to work with the fundamental theorem of calculus, which, as you know, any theorem that has a name is a big deal. But when the word fundamental is in the name, I think you can tell that this one really will make an impact on the mathematics that we're working on. Okay, so here we go. We're going to begin by talking about a function, y equals f of x. And that function happens to be defined on a closed interval ab. This picture here sort of demonstrates the piece of the function that we're talking about. A and b are values on the x-axis, and although I haven't explicitly stated it, this interval notation here tells us that a is less than or equal to x is less than or equal to b. So a is less than b for sure. And we're going to be concerned with values that are between a and b. So anything in here between a and b are values of x that we're going to be concerned with this function. So we're going to introduce a new variable t, and t is any value between a and b. And from t, we're going to make a function a of t, which would be the area under the curve between a and t. As you can see, I've colored it in green here. This is what I'm talking about, this space in here. So as t slides between a and b, the area under that curve will change. If I want to make the area bigger, I slide t closer to b. If I want to make the area smaller, I slide t closer to lowercase a. So I've got like a little continuous function here, which just computes the area under the curve. So far we've been using Riemann sums, where we use rectangles to approximate the area under the curve. But we found out near the end of the last lesson that if you take the limit as the number of rectangles goes to infinity of those Riemann sums, you get the actual area. And we've said that we can write that limit in this notation, which we call the definite integral. So if I want to find the area a of t, which is the area under the curve between a and letter t, I would simply do, oh goodness, here I am writing this all wrong. Let me get back to this, sorry about that. This would be the definite integral with a as the lower limit, t as the upper limit of f of x dx. So specifically, if we wanted to find the area of the entire region between a and b, we would write that like this. Area, capital A of b, would be the integral, definite integral from a to b of f of x dx. This is just notation right now. We really don't know what to do with this yet, but that's what this fundamental theorem is going to help us with. So let's proceed. As I mentioned on the last slide, we can move this letter t to any value between a and b, and it'll find the area under the curve at that point. So if I'm sitting at t and I slide it to the right just a little bit, say t to the location t plus h, we can find this area here from a all the way to t plus h. So that would be all of this stuff going all the way over to the purple line. Just to be clear, if this green t is my location for t, and then the purple dashed line is t plus h on the x-axis, then this blue distance in between them, that would be h. Right? T plus h minus t gives you h. That's how you measure distance on the x-axis. So h is just this little smidge of a distance moving to the right away from t. Okay, specifically, if I wanted to know that purple area all the way out to t plus h, that would be a of t plus h. And based on the notation we just learned, we could write that as a t plus h, the integral, definite integral, a to t plus h of f of x dx. And if I just want to talk about the area of this little slice here between t and t plus h, the way we would calculate that is we'd subtract the purple area minus the green area. So that would be a of t plus h, which was the purple area, minus a of t, which was the green area that we had a few screens ago. That equation would give us, or that expression would give us this blue area here, the little rectangle between t and t plus h. Now what's cool is h is a really small number. This little h here is a very small number. So I could approximate this value of this rectangle, just like we did with Riemann sums. It would be approximately equal to, oops, I used purple there, I guess it's okay, the width, which is h, times the height, which is f of t. Okay, let me show you again what I'm talking about. This little blue sort of rectangular shaped region can be approximated by pretending it is a rectangle. And a rectangle would be length times width. The width is just h, we talked about that earlier. That's this little distance here. And the height on the left-hand side would be f of t. So I'm going to write that out as an approximation. That the area a of t plus h minus a of t is approximately h times f of t. You can see here I've rewritten our approximate expression, approximation. I just flipped the sides around. So now h times f of t is on the left, and our difference a of t plus h minus a of t is on the right. And what I can do is I can sort of solve for f of t by dividing both sides by h, and this approximation would still hold. So what we're saying is that f of t is approximately a of t plus h minus a of t over h. And this thing here should look familiar. This right here should look familiar. That's the difference quotient for the function a. And what we're saying is that the difference quotient for function a is approximately equal to f of t. Well, we learned back in our earlier studies that if we take the limit as h approaches 0, we actually get the derivative of a. So we know this is true. A of t plus h minus a of t over h. That's that definition of derivative that we didn't really like to use for calculations, but it's important for actually defining the derivative. So I have this thing where if h goes to 0, I get the derivative. But if h goes to 0, my difference is actually just f of t, because there's no width on that rectangle. It's just the height of that left-hand endpoint. So what I can tell from this is that f of t is equal to the derivative of a at point t. And we learned a couple lessons ago that this implies that function a of t is one of the antiderivatives of our function f. So I could say that a of x is capital F, right, our antiderivative, plus some constant. If you take the derivative of a, you get f of t. That means that a itself is one of the antiderivatives. We don't know which one it is, so we have to put plus c on the end. But if you take its derivative, you get lowercase f. So our function a of x can be written as f of x, the antiderivative of f, plus c. Okay, so there's a connection here that we're about to make between our antiderivatives and this derivative f and the area under the curve. So the real question becomes, what is the value of this c? And if you remember back to our original picture, which I've copied here, the area under the curve as we move t, right, can be calculated. And if I slide t back on top of a so that there's no area, that area must be 0. What that means is that a of lowercase a is 0, right? If I slide t back on top of a so that there's no area under the curve, then the value must be 0. Well, we can use that to help us solve for c. And here's how we do it. We know that a of x equals f of x plus c. That means that a of a must equal f of a plus c. And since a of a is 0, we're talking about capital F of lowercase a plus c must equal 0. So c equals the opposite of f of a. So we now know what that constant is. It's the opposite of the antiderivative evaluated at letter A. Now remember, we said earlier if we wanted to calculate the entire area between A and B, then we would just slide t over to B and we'd have A of B, right? Capital A of B, which we could also write as capital A of B, which would be capital F of B plus C, but we already know what C is. And this is the cool part, that capital A of B is F of B, oh goodness, I'm going to run out of space, minus F of A. Okay, this is a big deal. So I'm going to get a blank screen here and rewrite this, and we're going to tie the whole doggone thing together. So here we have it again. The area under the curve from A to B, which we write as A of B, we just found out equals the antiderivative capital F of B minus capital F of A. And now here's the actual fundamental theorem. We call it part 2 of the fundamental theorem of calculus. This thing can be written as another notation. It can be written like this. The integral, definite integral from A to B of f of x is f of b minus f of a. This is huge. This ties everything together. We now have a way to calculate the exact area under a curve, which is this notation here, just by finding an antiderivative, plugging in b, implying an antiderivative, the same antiderivative, plugging in a. We know how to do all these things already. I'll give you a brief example to end this video, and then my next videos will be further examples. Okay, so let's say you're given a problem where you're asked to find the area under a parabola between x equals 1 and x equals 4. The notation for that is the definite integral, which I've written on the top here. This definite integral will help us find the area under this curve. And we now have a very specific way of calculating this. We just have to find capital F. And we have all kinds of tricks for this, but we're going to use our power rule for this one. The antiderivative for x squared, an antiderivative, is 1/3 x cubed, which is sometimes written as x cubed over 3. And we want to plug in b and then plug in a. So the notation we use is we draw a a vertical straight line, and we write a 1 here and a 4 here. And then what I'm going to do is I'll plug in 4 first. 4 cubed, I think, is 64. That's big F of B, minus a 1 cubed, which is 1, which is big F of A. Let me just note that this is capital F, with B plugged in, and this is capital F with A plugged in. And when you do that calculation, the area under this curve better be 63 over 3. And as you know, 63 over 3 is 21. So the area under the curve x squared, when you look at the region bounded by a equals 1 and b equals 4, is going to be 21 square units. There'll be much more on the fundamental theorem with examples coming following this video. Good luck.